Good morning.
Good morning.
Good to see you all. Let's talk a little bit about plans for the next little bit. We're coming up pretty close here on our next exam. So let's set that on Thursday again. The two options would be, actually, let me look at my calendar for just a second. No, it doesn't matter. The two options are this Thursday immediately next week or the Thursday after that. If we do Thursday after that, it'll probably be the same scenario as last time where we'll have advanced in class a little bit beyond where the exam covers. But that will give just a little bit of extra time for study. Anyone have any preferences? It doesn't matter too much to me.
Is that the last test or is there?
No, there will be basically some combination of final exam, end of semester tests that have components that are the material we've covered up to there, and with separate components that are comprehensive review of exam plans. So basically we'll end up with 3 in class plus the comprehensive part, but the third exam will be so close to the comprehensive exam that the comprehensive probably won't cover it. The comprehensive will be basically a review of exam plans. So any preferences on date next week or the week after?
Yeah, probably next week, so we don't start learning more material.
Okay.
Immediately.
Okay, go ahead and have exam this coming Thursday? Okay, that sounds fine. And we'll spend some time early next week making sure we remind you of exactly what topics we're handing out. Let me know how. Let's do. Ooh! Cheers, everybody. I didn't even
Cheers.
see it. Ooh, that's so good. Oh, that's a good one, thanks. That's funny. It just looks so natural to me, I didn't even see it. That was just popping sound. What's going on here? That's funny. How? So I wanted to get a little feedback on this most recent yesterday's lab and lab homework with the complex numbers. Are there any sticking points there that we need to look at? 1 or 2 questions from that that are worth doing together?
Number 48, I think.
Okay.
Yeah, 48.
Okay, 48? Oh, no, that's what we did in class. Yeah, the 48?
Oh, I think we listed it, yeah.
Yeah, so that was the theta, it's plus theta plus I, sine theta, and then take the complex conjugate of that and add and subtract. Yeah, so that's exactly what we did together on the board.
Those are the 2 things you want us to remember.
Yeah, that's right. Yeah, but know where they come from. Anything else, or?
I have a question.
Go for it.
Any of the 19 through 24, it just says find all solutions of the equation. I mean, you wrote on there, but if you didn't write on there, how would I know what to actually do? I mean, mathematically, you can come up with, you can do a derivative, you can do all kinds of.
No. So these are all basically quadratics, with the only exception of number 20. So all of these are in the quadratic form. You're just using the quadratic formula to solve for the 2 roots. That's
So
it.
you're just keep your mind on complex numbers when you're.
Yeah. The only point is that some of these will have complex roots because you'll have something under the radical that's a negative, and then you can factor out the negative and write it as an I.
Right.
That's it. So the only one of those that's exceptional is the 4th root of x equals 1. So if it was square root of x equals 1, then the answers would be plus 1 or minus 1, right? But it's 4th root. So now that's saying the square root of, well, let's look at it a little bit together. Okay, so in fact, that actually ties in that actually ties into something that I'm wanting to go a little further on today. So we'll come back to that. Anyway, the point is that the only one out of that whole group of questions that wasn't just application of quadratic formula was that.
Okay.
Good? Let's have a look. Okay, sure. So number 29, we've got z is root 3 plus I, and we've got some other complex number which needed a name for it, so we're going to call it W. Nothing special on it. That is 1 plus root 3I. So we're asked here to find polar forms for ZW, Z over W, and 1 over Z by first putting Z and W into polar form. Okay, so this is great. Basically speaking, we are going to find R and theta for the various combinations ZW,
Thank you.
Z over W, and 1 over Z. Did I remember that correctly? Okay. Now, there are a couple ways that we could do that. And actually, this is going to be a perfect place to lead us into what we want to talk about today. So this is a good question. We could do it the way that we did it last time. And that would look like this. Okay. So find R and theta, or let's look at this one. Let's look at Z over W. For Z over W, so we have root 3 plus I over 1 plus root 3I. Okay. So in this particular case, let's start off doing this the way we did it last time. And then we'll show you a neat way to do it alternatively. So the way that we did it last time, we said you're going to try to get rid of that imaginary number in the denominator and move all the imaginary numbers up to the numerator, right? So what was our technique for doing that?
Taking the complex.
Yeah, multiply by the complex conjugate. So we're going to multiply by the complex conjugate of the denominator. We're going to put it in the top and the bottom so that we're just multiplying by 1s. We're not changing anything. What's the complex conjugate of that?
1 minus.
That's right, 1 minus root 3I. And if we multiply by that on the bottom, we've got to multiply on the top as well so that we didn't really change it. It's still equal to what we started with. And the reason, of course, we're multiplying by the complex conjugate of the bottom is because we want to get rid of the imaginariness of the bottom. We want to move all the imaginariness up to the top. Okay. So equals, what's in the bottom here?
1 plus. Yeah, 1 plus 3.
That's exactly right. Very good. So it's always real part squared plus imaginary part squared. Remember that? Because it was the complex number squared is the magnitude. The complex number times its complex conjugate is the magnitude of the complex number squared. Now, we can do it just, the long way as well. This times this is 1. This times this, and this times this cancel each other. That's the whole point of the complex conjugate. And then this times this, we've got minus I squared, which becomes plus, and then root 3 times root 3, so 1 plus 3. Now let's do what's in the top. So in the top, we're just going to have to multiply everything out. In general, we're going to have 4 terms there, right? So why don't you go ahead and expand out that top, do it on your notes there, and then I'll do mine on the board here. Let's compare. Everyone matched up? Check, good. Okay. Let's group similar terms together. Here's our real terms, let's add them together. So that's going to be twice root 3 for combining those. And then this minus that, that's going to be minus 2i. Good. And then divided by 4.
Could you simplify the 2 and the 4?
Yeah, let's go ahead and do that. So let's do root 3 minus I over 2. Perfect. Okay. So let's read off our x and our y. What is our x?
Root 3 over
Root 3 over 2, good. What is our y?
-1, or just 1.
Be negative.
Yeah, the whole thing. Everything that's next to the I. So the half is important. Now, in our complex plane, see if you can find the location of that point. So in our complex plane, we've got -1 plus 1 plus I minus I. So the x part is root 3 over 2. Root 3 is about 1.7 or something. Over 2, so 0.8, 0.9. So it's going to be along there. And then minus a half for the y direction. It looks like we're about there. Now, you may or may not have noticed here that this problem is kind of hinting at a special triangle. There are a couple triangles that pop up commonly enough that they're worth kind of noticing. This is the 30, 60, 90 triangle. So the 30, 60, 90 triangle is a very common triangle. 30 degrees there, 60 degrees there. It doesn't matter which way you turn it, of course. And 90 degrees there, let's label it. And it happens that the sides of that triangle go like two there, 1 there, and root 3 there. So notice that this does obey the Pythagorean formula. If we square that, we get 3. If we square that, we get 1, and 1 plus 3 is 4. And if we square that, we get 4. And of course, you can scale that triangle as you like, meaning multiply all the sides or divide all the sides by the same number, make it bigger, smaller, and the angles stay the same. To confirm that that really is the 30, 60, 90 triangle, which is not obvious unless you know it, you just have to use the normal trig function. But if you have your calculators here, let's confirm that. So sine 30, look at, if this really was 30 degrees, what would the sine of that angle be?
1 over 2.
Yeah, 1 over 2, opposite over hypotenuse. So let's put question mark equals a half. Does that check out?
Yeah.
Okay. So this really is the 30, 60, 90 triangle. And again, I don't ask you too often to memorize things. But at some lower level of priority, that's a worthwhile thing to have in your data banks. It pops up pretty commonly. What's that?
Big.
So, well, I want you guys to sleep well. You need your rest. There's another triangle that pops up with some regularity, the 3, 4, 5 triangle. The 3-4-5 triangle is interesting, and it gets used commonly for examples because it's integers that obey the Pythagorean theorem. 4 squared is 16, plus 3 squared is 9, equals 5 squared. But sometimes people get those two triangles confused with each other. They see the 3, 4, 5, and they try to write 30 or 60 degrees on it. That's not correct. The 30, 60, 90 goes with these things. Yeah, so anytime you see root 3's flying around, somebody's trying to point you towards the 30, 60, 90 triangle. And they've done that in this case so that the numbers will kind of work out nicely and convenient. So, in fact, if we zoom in here a little bit on that diagram, we know that it's in the fourth quadrant, and we're over a little bit more than we're down. So that is here, and the sides of our triangle are 1/2 and root 3 over 2.
Aren't we actually down more than we are over?
No, we're over.
No.
It's catchy. Everyone happy with that? Okay. And what would this side be in this scaling?
2.
Yep. Yep.
Oh, this is
We've scaled our triangle relative. It's slightly different. Yeah, 1. So this would be 1/2 squared is a quarter. That square would be 3/4, and together would be 1 squared. So basically, like I said, you can scale everybody as you like. So in particular, it looks like we immediately have our answer to this question. We immediately have our answer to this question, which is R equals what? 1. And theta equals what? What's this angle right here? 30. Okay, so what's theta then in the way that we normally measure it?
300.
Sorry, say it again.
5%.
Yeah, 30 is, this is pi. That is pi over 6. That's right. Yeah, correct. The question I'm asking immediately, although we will need to convert to radians, the question I'm asking immediately is what is that?
300, right?
Yeah, 330. So theta is 330 degrees, but correctly noted, we really don't want to leave it in degrees, because if we're going to write it as the exponent, that's a literal exponent. When we put something inside a trig function, you can interpret it in degrees or radians or whatever you like. It's a function of that thing. When we put it up in that exponent of e to the I, that's a literal exponent. And it only means the thing it's supposed to mean in radians. So, let's do it the way you suggested. I think that's good. That'll be a nice, quick way to get the number we need. So it's 2 pi all the way around. Take away the 1/6 of pi. And so this part here, that 180, that was pi. This 90, that was pi over 2. And we divide it into 3 equal slices of 30. So, so 1/3 of pi over 2 is pi over 6. So let's get a common denominator here. So our common denominator, let's say, is 6. So, so what do we end up with? 11 12ths pi. Yeah, if we do it the normal way. Okay, so Z over W, this weird thing here that we were writing, which was that, is literally equal to 1 e to the I 11 pi over 12. Did we miss something?
Should be 11 over 6 pi.
So
Yeah, sorry. The 12 was there, the 6 was there.
you also wrote it down in.
What else did we?
You also wrote it down.
Yeah, that's right.
You got
Yeah, 11 6, thank you. Okay. Okay. Now, this is going to segue beautifully into the start of the other things I'm going to show you about the way these numbers work. There was a little hint given to you in the outline for that question. It said you'll be able to calculate these things actually more quickly if you put Z and W into polar form independent. Do that from the start. So let's go back. So Z and W. Z is √3 plus I. W is 1 plus √3I. Let's get our complex plane. Let's put that 1 minus 1I minus I. Okay, what I would like for you to do is to independently, those two numbers, each of them, put a dot in the complex plane where each of those go. And then write its language. Let's check where our two dots are. Okay, so Z, that's positive in both X and Y. So Z should have ended up in our first quadrant here. It looks like our Y is equal to 1, right? So we're somewhere along there. And our X is equal to √3, which is a little bit beyond 1, but shy of 2. It looks to me like Z is there. What is that radius, by the way? That's right. That's 2. And that angle is what? 30 degrees. Are we agree with that? Perfect. W, it looks like both of these are positive again, actually. Except now the X is 1 and the Y is 3. So W is up there. What's its radius? 2 degrees. Yeah, and its angle is? That's right. So that one's 30. Okay, good. Now, let's write it in polar form. Z equals and W equals. Write each of those down in the R e to the I theta form, converting to radians. Okay. Check yourself. We'll keep working for a second or two. We're still looking at it. Good. Good. Now watch this.
What did you do to get the two EI pilots, both of the Z there? Is that what we already have?
It's a, yeah. So this is our polar form, R e to the I theta. Now, that should seem a little mysterious to you. You're allowed to be a little skeptical of it. That is super weird, and I haven't proved it to you. We're just working with it for now. I have assured you that that is literally a representation of the complex number. I haven't proved it to you yet. We will get there. But that's the form. R e to the I theta. You'll have to send me just a little loaner on credulity suspension. Incredulity suspension. So whatever's in front there is the radius. Whatever's in the exponent next to the I is the angle. Very good. Okay. Now watch this. What happens next is actually kind of amazing, and it's one of the reasons that this polar form for complex numbers is so handy. Let's do Z over W. That's what we calculated before, right? We went this way. Now let's go this way. And one of the things I like about math so much is that if you do it right, you get the right answer. And there are sometimes a few different ways to do it. So Z over W, I'm going to write that as 2 e to the I pi by 6 over 2 e to the I pi by 3. Okay. How would you recommend simplifying that? Well, for starters, what next? Well,
We still want.
that will change it. We don't want to do anything that would change it. We just want to simplify it.
So it's find common denominator for pies.
Maybe, depending on what you mean by that. How should I rewrite that? Well, dividing by something is the same as the exponent being 1. Let's write this as e to the I pi by 6, e to the minus I. Know that? Yeah. What would you do next? I have a product of things that are to the same base raised to different powers. Add the exponents. equals e to the I pi. Sixth minus the third. So the common denominator on that would be a sixth, right? So you got 1/6 minus 2/6, so we end up with what? Negative 1/6. So e to the I pi negative by 6. Okay. And we've already done this calculation, right? What did we end up with?
1 e I 11 pi over 6. E to the I 11.
Yeah. And what did we do when we went this other way? Did we get the same answer? We screwed it all up? I think so.
A negative rate
I think it's
is
just
the same thing, so.
Yeah. What's the thing about sines and cosines? They're periodic. So adding 2 pi inside a sine or cosine always gets you back where you started, right? It's the same thing. So look what happened here. I'm actually really glad it turned out this way. When we did it originally, we said plus 11/6. Now we said minus 1/6. Are we in the same place? Same answer. Beautiful. So actually, this is a worthwhile thing to notice. There's lots of ways to write these things, in a sense. Plus plus any numbers of 2 pi's. Going around by 2 pi for n is any integer. Any numbers of 2 pi's get you back to where you started. That's just saying that sine and cosines are multi-valued functions. What I would like for you to do next real quickly. Write the polar form for those two things. Gotcha. What do you think we should write it as?
2 e I pi.
No. No, this can't travel. But e to the I pi over 2, where is pi over 2 located in the complex plane? Straight up. What number is that? What's
In degrees.
Yeah, you
it's 90 degrees. What number is straight up with radius 1 in the complex plane? No, straight up. Straight up. Vertical axis, y-axis, complex axis. So if I have radius 1, what number is that? It's my x-axis. It's 100% real. What number has magnitude 1 lying in the plus x-axis? 1. What number is that? I. I. Just I. E to the I pi over 2 is I. What is that? Negative 1. Negative 1. Yep, and what's that? Negative 1. So if I wanted to simplify this even further, I would just write it this way. Yeah, but don't forget the this, e to the I pi over 2, is the complex number. Forget the 4 for a second. With what radius? Do you see the number sitting there right next to this? You see it sitting there? It's a 1. That's right. What radius? 1. Pointed straight up. What number is that? I. So now with the 4, altogether, what number is it? Yeah, right. This one, the pi by 6 doesn't simplify quite as nicely, but we could write it back in this form. That's basically what we would be doing. We were told to put it in polar form, so I guess we really wanted to leave it in polar form or something like that.
So why were you able to reduce the because it's straight up?
Because it was straight up, it was 100% imaginary. So this just became a convenient way to write it. You could say I was writing it in the x plus iy form. It's just that x happened to be 0. And if you like, just as a check, we can go back and do that explicitly. If we do that explicitly, what do we get? ZW is root 3 plus 1 plus root 3i. Let's multiply out. Root 3 plus 1 sorry.
That one's an I.
That one is an I. Let's try that. Okay. Root 3. What's this? What's these two terms together?
3I.
Okay. So we've got this and this. Now let's do this
I.
and this.
Square root of square.
Sorry.
Root of 3i squared.
Square root of 3i squared, otherwise known as
Negative 3.
negative square root. So that and that cancel. That and that. Now I want to do something really weird. I'm going to ask you a question. Well, for starters, what is I? I mean, what is I?
Square root of negative.
Square root of negative 1. Have you ever wondered if I has a square root? We have to make up a new letter. Should we call it Q or J? Yeah, this is related to the question that we did earlier in a way. It's not exactly the same question. Is that a thing? I want to show you how to think about it. This is a really powerful way to think about it. Do it in a couple steps. First, let's think about it as I to the 1/2 power. That's square root, right? Next, let's rewrite I in polar form. What is I in polar form? What's that?
I0.
Okay, so R e to the I theta in polar form. I in polar form. So what's the radius? How far is I from the origin? What's the magnitude of I? 1. And it's straight up, right? So what angle is that? 90, now in radians. Pi over 2. Okay, so let's write that as e to the I pi by 2 to the 1/2 power. Okay? If that's all we do, we're going to miss some roots. We're only going to get 1. This is a square root. How many of them should there be? So the way to make sure that we get all of them is to include all the different ways of writing I. Remember, you can always add what to the exponent? To the exponent, the real part of the exponent, e to the I. You can always add that. You can make full loops, full laps. You can always add 2 pi to the angle. So I'm going to say pi over 2 is the phase, but n 2 pi, I add any number of 2 pi's where n is an integer. Sorry, that's a little small. If I add n 2 pi's, now I've still got my I there, right? I drew the brackets, I is multiplying everything. But if I add n 2 pi to the angle, things are still the same, right? Now, I have something to a power, and then that whole thing to a power. This kind of reminds me of something we did earlier this semester. What's the rule? Multiply the powers. So I should write this as e to the I pi by 4. What's n 2 pi divided by 2? Now, what values of n, this should work for any possible value of n, right?
Not any.
As long as n is an integer. Any value of n is an integer. Should work. What would be the simplest choice for n? I think that's right. Yeah. What would be the next choice naturally after 0? 1. What would you choose next? Okay, but I want you to notice something. If I choose 2, then I've got 2 pi there, which means 2 is the same as, no, it's repeating. Same. Next I could choose 3, but 3 would just be repeating that. So the only ones that are worth choosing that are different from each other are what? 0 and 1. Okay, so I'm going to claim that root I is equal to, well, how many different ones did I get before they started repeating? 2. How many answers do I expect for a square root? 2. It's almost like that's so I'd have e to the I pi by 4, and then I would have e to the I pi by 4 plus pi. What's 1/4 plus 1? Yeah, otherwise known in fraction, an improper fraction. Yeah, 5/4. Sorry, that's not a minus. It should be.
And I don't know if it
I don't know. Sometimes my fingers operate. Okay, now, what are these? Well, let's look at it in the complex plane. Yeah, there's numbers. They're complex numbers. And they have a real part and an imaginary part, it turns out. But let's locate them in the complex plane. First of all, what's the radius of these two numbers? You all see the radius sitting out front, right? Okay, you got used to that one, good. The radius is 1, pi over 4. How many degrees is that?
That's 45.
45 is their answer. So that's there. And then if I add pi is how many degrees?
180.
180. So then the other one was plus a 180. That was over here, right? So if that magnitude is 1 and that magnitude is 1, does anybody know the two sides of a triangle with a 45-degree angle?
45, 45, 30.
Yeah. Yeah. Which is the same thing you just said. So if I square that, and I square that, half and half is 1 squared. And this one, I'll write the sides as positive magnitudes. You can see from the graph it's down and over. So it looks like my two roots are 1 plus I over root 2. And whole thing minus. And last thing, let's check if that really makes any sense. How should we test it? How should we test if that's really the square root of I? I agree entirely. What math would you suggest we did?
Negative 1 square root of
Okay, so square it and see if it gives us back. If that is the square root of I, when we square it, we should get. So let's test it. 1 plus I over root 2 squared. Let's see. We're going to have 1 times 1, right? Now, the root 2 times root 2 in the denominator, that'll become a 2. We have 1 times 1, what's that? Then we're going to have 1 times I, what's that? I, and that will happen twice, right? Both combinations. So plus 2I, and then we're going to have I times I, what's that?
I squared.
I squared, otherwise known as negative 1. What's that?
I want to.
So we don't need to go any further than the complex numbers in some sense. All of our roots will be covered. Even the roots of the complex numbers will themselves not take us outside the space of the complex numbers. We don't need to make up any new names for square root of I. It's just another complex number. And we can take square roots of all kinds of things. And cube roots. And ninth roots. Well, if you really want another symbol, and you're just really keen on it, I would suggest that you go look at the Wikipedia article on quaternions and octonions. But once you start doing that, you're going to lose very familiar properties of numbers like their commutativity. We're very much accustomed to A times B equals B times A. There are some numbers that don't operate that way. When you switch them, the product changes. In fact, we've seen kind of one example. We saw that the cross product gets a minus sign when you flip the order, right? we're gonna start learning about matrices before too long. If you have two matrices, the order in which you multiply them can be very important. There's something completely different if you flip the order. In fact, by the way, that principle is one of the most important principles in the field of physics called quantum mechanics. That when you multiply two things, the order in which you multiply them matters very much. Not for normal numbers, but for matrices, for example, and other numbers that are matrix-like operators. Okay? Okay.
What does a matrix look like?
Kind of like matrix. Yeah.
Well, it's not equal.
This much stuff.
That's the. Sound like it.
Would you like more dice?
If you're not gonna drink it, I'll be happy to take it. That was an excellent joke.